Welcome, Professor Asheesh Kumar Singh, sir, Department of MNNIT Prayagraj, a renowned academician and professor in Electrical Engineering Department. His research expertise span across deep learning based fault and mobility energy integration distribution system. He has significantly contributed to the academic community with numerous books, journals, public. Professor Singh is a senior member of IEEE and has actively contributed to IEEE Power and Energy Society and other numerous professional bodies. He has played a key leadership role at various posts like head of Electrical Engineering Department at MNNIT Prayagraj and has organized multiple international conferences and short-term courses.
विजय जी, मुझे लग रहा है कुछ कुछ ऑडियो इश्यूज हैं, आवाज साफ नहीं आ रही है शायद। क्या विजय सर, am I audible? Hello.
Hello.
Yes, sir, you are audible, sir.
Okay, thank you, Abhishek ji. Well, so I have given a time of 1 hour approximately to share with you. So let me share my screen with you to start on this topic. As the topic of the FDP is, just a minute, launch meeting क्यों कह रहा है ये? हेलो
हाँ सर, गुड मॉर्निंग।
जी जी, नमस्कार। ठीक है सर, सॉरी, मुझे लग रहा था कि शायद आवाज नहीं जा पा रही है।
नहीं आ रही सर।
Thank you very much, Dr. Vijay, for the introduction. And this is an FDP on opportunities and challenges in modern power system. Basically,
Yes.
I appreciate lecturing department of REC Kannauj for selecting this particular topic. As we all know that our power system is in transformation stage since previous 2 decades, or rather you can say more than 2 decades. Earlier, the power system was a very easy system. It was claimed as the largest man-made system. The system which was having its presence globally in all continents, and it was also interconnected system where generation was taking place at one geographical location and the consumption was taking place in some other location with the proper connectivity of an interconnected power system through transmission lines and distributed generation. Then distributed generation came, then the opportunity for environmental protection came, and we started integrating the renewable energy resources, right? And this was an opportunity which we enjoyed. Yes, this was giving us a benefit of some greenhouse gas reduction, which was going to be a big challenge in view of climate change happenings in our surrounding. But with this integration of renewable energy resources, another challenge was it was intermittent in nature and it was not possible to make it dispatchable and make the conventional sources redundant to fulfill the energy requirement of the globe. Then battery storage came. Battery storage was sufficiently capable of making the renewable energy integration dispatchable in a way that whenever there was an excess generation, it was being stored, and whenever there was an excess load, it was being released or discharged. So in this way, the challenges keep on increasing. But then second opportunity came through the electric vehicle for towards the direction of making the transportation electrified. It was claimed that transportation was the largest source of environmental greenhouse gas emission and its destruction. So they decided, few of the countries presently, they have decided the timeline also. Okay, after 2030, or in some few countries after 2035, they have decided that they will produce all electric vehicles only, and there will be no production of the IC engine based vehicles, which are uh, producing the greenhouse gas emission. Well, wonderful. Then for electric vehicle, we found that there are certain challenges for the requirement of battery manufacturing, because it was using some typical sort of minerals which were not equally distributed across the globe, and there were few global locations, geographical locations, where these minerals were in abundance. So all those things made a prominent impact on the policies related to the batteries to be used in electric vehicles. And initially, there was a challenge that these
Sir,
batteries were very.
sir, sorry
Hello.
to interrupt.
सर अभी स्क्रीन शेयर करी नहीं थी शायद मैंने. अभी मैं
अच्छा,
कुछ इंट्रोडक्शन पे ही बात कर रहा था,
ओके, ओके.
और मैं स्क्रीन शेयर कर देता हूँ सर. सॉरी. अगर ऐसा है तो मैं स्क्रीन भी शेयर कर देता हूँ. जस्ट ए मिनट. अभी मैं कुछ आपको टॉपिक से और उससे कुछ जो आपने टॉपिक दिया था चैलेंजेस वाला, आई वाज जस्ट trying to you are screen sharing.
जी, 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 सर.
Is it visible now?
Yes, yes, sir.
Good. Let me press Control L for this. So this is the topic which I'm going to speak. But let me introduce with the connection of this title with the topic of FDP. I was trying to connect those things. So how these challenges of the modern power system, they came to us as an opportunity to improve the challenges coming on the daily basis, for the making the system more reliable, making the system more environmental friendly, and making the system more compatible for fulfilling the load requirements. So in that process, we found that batteries are a very good friend of the power system, but it was also observed that the recycling of these batteries is going to be a difficult uh, thing in future, as earlier the lead acid battery which was being used in the vehicles and these inverters in our houses, they were 100% recyclable. That was the very positive point with them. But later found that due to some excellent characteristics of the energy density and power density, these lithium and batteries were uh, quite friendly, and they were in use in abundance for all these electrical applications. In general, they are having a sufficient lifespan, right? But it was found that in electric vehicle batteries, they are not capable of use for automotive use specifically after a sufficient time, that is 8 to 10 years. But still, as per the shelf life of the life cycle, you say there was a total time or lifetime of the battery was around 15 to 20 years, depending upon its uses, right? So, as there were some other concerns related to the recycling and the environment were concerned. So it was a challenge how to use these batteries, which are a costly asset, and how to utilize their remaining part of the life, which is around 12 to 10 years, for the some other alternative application. So here the term second life battery is related to this concept only, right? And it was very important to use them for the sustainability and for other climate concern. So let me start. What is second life of battery? As I've already told you, lithium ion battery has a calendar life of 15 to 20 years, depending upon its ambient conditions. Key features of lithium ion batteries are high energy density, long life cycle, low self discharge, that is, retains charge longer, even if not in use, and no memory effect, that is, it is going to give you a consistent performance, not depending upon the memory that it was used last time, it was used for only this duration or only for this depth of discharge. No, it can be used uh, consistently throughout its lives. But we all know that it is a proven fact that the battery cycle life decreases with increasing depth of discharge. So there was a definition given by this US Advanced Battery Consortium, which is given in 1996, that electric vehicle batteries are to be retired after reaching the end of their useful life in vehicles. That was given on the basis of experience, that was given as 8 to 10 years, right? And on the basis of original capacity, it was also decided after this 8 to 10 years, their original capacity reduces to 70 to 80%, right? And this is basically given as the end of life of battery for the automotive purposes, because now it is not capable of giving that much power which can fulfill the requirements of the battery. Oh, sorry, electric vehicle. But even at the 70 to 80% of the original capacity, they are still useful for some alternative purposes. There was a sufficient research literature available on this. What are those alternative purposes for which this second life of the battery can be efficiently and economically utilized, right? So I'm saying these two typical characteristics for this: efficiently and economically, right? That we will discuss in later slides. So it was said that in case of PHEVs, these battery can go beyond 70 to 80% or below to that capacity also. It was established in some literature. Reason being, there was an ICE engine available to support the performance in case of hybrid vehicles, right? So PHEV is plug-in hybrid electric vehicle where this battery can be charged through some plug, right? So this is a direct connection with the full battery electric vehicle. In case of battery electric vehicle, there is only battery which is getting its power from the outside, means grid. Second is plug-in hybrid electric vehicle, means it is also having a battery, right? And it is not, in case of hybrid electric vehicles, the battery charging is dependent on the performance of the IC engine, function of the IC engine. But in case of plug-in, the battery is discharged from the outer source, which is dependent on grid or some charging station, right? So for the PHEVs, this range of 70 to 80% is either it may go below 70% also, because there is an IC engine to support the performance. But we all know that there are some psychological factors such as range anxiety, right, which are always considered as a this for the fear factor for the drivers. So these psychological factors, they force the drivers to replace the batteries as per the given guidelines. So few of them also replace at 70%, or few of them may go beyond 65% or 60% like this. But this is clear that after this much duration and capacity degradation, these batteries are going to be replaced or out of service of the electric vehicles for with the new batteries. Now, what to do with these batteries, right? So, with immediate disposal, that is, either you discard it, throw it, or you recycle it. The retired batteries are repurposed for those applications which are less intensive in energy demand, right? So what are those applications? Those applications are given as stationary energy storage. We all know that electric vehicles batteries, they are considered as battery on wheels, right? And there are some stationary energy storages which can be useful for integration with renewable resources to balance the supply and demand on the grid and provide backup power during outages, right? And there are some ancillary services also like grid balancing where they can be used. And these repurposed batteries, this concept of repurposing of battery before recycling, that is called second life operation of the batteries. And these batteries are called in that stage, they are termed as second life batteries or SLBs. Now, I have told you two different terms, right? So, one term is the repurposing, and second is the refurbishing, right? So, in case of repurpose, what we do, we take the complete battery out from the electric vehicle and we immediately repurpose it for some second life application, means we use it directly, right? So, it is always a ready to use approach. It can be used with the native battery management system. It can integrate further elements. Means if you need to manage the voltage, so you can use some series parallel connections accordingly, right? But in all such cases, every such battery is having its own battery management system, but a overall master battery management system is required to manipulate all these local BMS. So what happens in this process? The complete battery requirement set becomes bulkier, right? And as these batteries may be of different manufacturers, may be of different year of manufacturing, may be of different chemistries involved in that, so their performance are difficult to be verified. Okay, just a minute. Well, so what happens in this process? They becomes bulkier. But what we do in the case of refurbish, we simply after the end of life of battery, we take it outside. Then we dismantle them. We open the modules, their body, and we remove the cells. We select what cells are useful, what are not useful, and accordingly, with the classification of the capacity, we reconnect them. And we make some series parallel connections to make a required voltage or current requirement, and then we combine them as a single unit. So what happens in this process? The battery size is reduced, right? So that is the basic difference between this refurbishing and repurposing. So repurposing is faster, simple integration, but bulkier. But in case of refurbishing, more effort is required before making it ready for the second application, but it ensures reliability and standardization. I hope you are aware with the term depth of discharge. I am explaining it here with an example, right? A 100 ampere hour battery discharge for 20 minutes At 50 ampere, the depth of discharge can be given as 50 ampere, means ampere hour on the denominator, that is 50 into 20 by 60. Battery was capacity was 100 ampere hour. So in this process of discharge after 20 minutes, that ampere hour by ampere hour, this becomes 16.67%, right? For being it converting into percent, we multiply it by 100. So what happens in this case? We can say that if depth of discharge is 100%, means battery is empty. If depth of discharge is 0%, battery is fully charged. Okay. So these are the few terms which we will continuously discuss in our presentation, right? So DOD impact on battery life, that says that higher DOD reduces battery lifespan. Frequent deep discharges cause faster degradation. That is the reason the vehicles which are used for commercial purposes, their second life of battery is quite shorter, right? And but the vehicles which are used for domestic purposes, means they run sometimes and they are used for shorter distances, means depth of discharge is lesser. Their second life can be a longer one and their performance can be a better one in the second life. And this is the very purpose where this reuse and refurbish, which I discussed in the last slide, that comes into picture, right? And similarly, this cycle life dependency is a parameter, temperature and battery lifespan is a parameter. So we all know that high temperatures, they cause overheating, accelerating chemical reactions and reducing battery lifespan. Whereas cold temperature means less than 0 degrees centigrade, they have higher voltage needed to charge, and they lead to stress on the battery because we are charging them on higher voltages. So the best practices which are suggested by the manufacturers along with the manual provided with the battery, they say that keep batteries in a mild temperature range for optimal performance and longevity. This is cycle life, right? So if you are using a battery for 100% DOD, it may end, its capacity may end in 200 cycles. For with 50% DOD, it may go up to 500 cycles, right? But if you are using it for 30% DOD, means lesser depth of discharge, the number of cycles may increase and that may go beyond 1200 or 1300 like this. So this is the impact of depth of discharge on its cycle life, right? So let me tell you one thing, there are two different terms which we will use here. One is calendar life and one is cycle life. Calendar means number of years in operation. Cycle means number of charge discharge cycles. Clear? Similarly, there is a term that is SOH, which is useful in deciding the battery operation and its use in second life of battery. That is defined as the percentage of initial energy capacity that is left in the battery, right? And it is calculated as a function of battery age and battery is in which manner it is being used, right? So if we say that it's a function of battery age, means slightly higher degradation rates in the initial years, here, clear? And on an average, it reduces like this, right? So this portion you can see it is a quite non-linear portion in between. Otherwise, remaining portions are almost linear. Clear? So this is the function of manner in which battery is cycled, means charge discharge is done. That is also a parameter which decides the battery SOH. Clear? And if we say what is the temperature impact on SOH, means higher temperatures, they accelerate degradation because they catalyze the chemical operation happening inside the battery, right? And there is a study of by Smith, Markel, Kim, and Pesaran that says that a 5 degrees centigrade temperature rise reduces state of health by 3%, right? And for their study, they considered this 10 years of duration at 54% of DOD, assuming one charge cycle of charging and discharging every day. So why second life battery is important means, and why their repurposing is required, because there are some environmental benefits. They say that battery life extension may reduce electronic waste. This may lower the demand for new battery materials, right? Because second life in the first life of the battery was in electric vehicles. Second life of the battery is in the battery storage, right? So it is a cyclic process which is giving you a complete supply chain before the recycling of the battery. And advantage is that when these batteries are being used in their second life, their cost is also reduced, right? And they are sufficiently capable of fulfilling the requirements, means that 20% decrease in the capacity is not going to hamper their performance. Rather, in studies, they are found more economical in terms of their utilization versus their reduced cost, right? So that's why these things are being promoted nowadays for completing the battery its complete calendar life of 15 to 20 years before recycling. Economic advantages are for this repurposing that second life batteries, they offer a cost effective energy storage solution. I told you that the cost is reduced, right? In this way, the utilities which are nowadays using storage as a major operation, in some Australian case studies, it is found that they are struggling for making an 8-hour backup of their utilities with the battery storage only, right? And their effort for making the power system more useful, more reliable for the end user. And that is basically what they are doing. They are integrating and making this support of the renewable energy with these batteries more utilizable, right? So this, in this way, what is happening, this all is basically promoting the sustainability, right? What is sustainability? Sustainability is means using lesser number of natural resources and making them available as it is intact for the next generation. Clear? So that is the purpose of the sustainability. I advise you to read about the term sustainability, and the related term is the Sustainable Development Goals of the United Nations. Clear? So this you can study and found that you can find that your future research, if you are a research scholar or teacher or academician, right? So you may explore these directions for your future research, and you will find that IEEE Explore is having a dedicated section on the climate change, on sustainability, right? And they try to include those related researches in the conferences as well as journals, right? So you shall focus this direction also if you are not doing presently, right? So what is circular economy approach? It follows the 3 R's, that is reuse, refurbish, and then recycle, right? And earlier this reuse and refurbish was not there. Use and recycle. So this was not a circular economy, it was a linear economy model. Clear? And now, under the impact of promoting sustainability, they are advising you to follow the circular economy approach by replacing older linear economy approach. You can find such diagrams if you want to explore, if you will explore about the term circular economy. And this is a recent article of 2024, I think January, February magazine of this IEEE Industry Application magazine. This clearly gives you a second life battery life cycle in circular economy, right? So the start point is the battery design and manufacturing in its before its start of first life, right? So what happens? The battery is designed, manufactured, and then it is used either for electric vehicle or they use it for battery swapping. Battery swapping is a different mode of providing charged battery to the electric vehicle. I hope you are aware with that. Clear? So what happens when you take these two batteries in different applications after the end of first life, right? So this battery is deassembled, right? Or you may use it for visual inspection, right? And if the batteries are damaged, right, you'd find that they are damaged and they are not usable, they are directly sent to recycle. Clear? Now, there are few things which you cannot inspect visually, right? So there is a state of health. If you feel that the battery is not damaged, but you have some doubt that the state of health of the battery doesn't seem good, there are some marks on the anode and cathode which indicate these things. Clear? So if you find that, so there are some different methods of the SOH estimation. There are some classical methods, there are some data driven methods, right? And by that you can decide it is having a sufficient state of health, right? And depending on that, you decide it can be either directly repurposed or it needs a refurbishing, means it needs to open it, select the useful cells, and throw out the remaining cells for the recycling, and then make the pack according to the requirement in its second life. So this repurposing is again, this product is designed and then SLB products are manufactured, and then again they go in the process of sales and commercials to the second life battery applications, right? But in the process of refurbishing, these packs are dismounted, modules they are dismounted, cells are tested, useful cells are kept for use, and then this modules, useful modules, they go in this cycle of again marketing, testing, product manufacturing, commercial uses, second life battery application. But which after dismounting these batteries, which are not found useful, they decided as damaged modules and cells, and they go for recycling, right? So this is a complete circular economy framework, which is a core of the sustainable efforts towards achieving the sustainable goals, right? And how this power system professionals, they can contribute to this, right? So this particular diagram explains you a complete setup, but it is not that easy to work. Basically, as an engineer or power systems, we will have to find out opportunities for us to work within this framework. So where are the opportunities? Opportunities of research are here for this SOH estimation. Opportunities of research are here for developing business strategies which are going to be useful or beneficial. Opportunities are here for developing a framework which can give you a direct monitoring right from the manufacturing of the battery to its end of life for recycling, right? So in that case, what will happen? There is a concept, they say that digital passport for the battery, right? So what is that meaning? Means whenever this battery will be manufactured initially, it will have a passport sort of register where all these informations will be saved, right? And they will carry with the every event of throughout the life of the battery will be recorded in that. And then here this SOH estimation will be easy to get directly by putting it some machine or some interface. You can find the information. Okay. So I have told you sufficiently about the climate change, how this climate change is connected with these things. Now let me tell you about the volume of the challenges in this process it is expected that the global EV car sales is going to increase in this way between this up till this 2035. Means by 2030 nearly 40 million electric vehicles will be there, and this will increase by 150% by 2035 in next 5 years only. And let me make you very clear that this projection is only for the cars, right? If you visit this IEA website, you will find that there are projections about the four-wheelers, six-wheelers, or larger trucks also. You will find these projections for two and three-wheelers separately. So this particular data is not considering those two and three-wheelers or the larger buses and trucks, right? Those numbers are apart than this, right? So this we all established on the basis of this data that the future of mobility is electric, right? And only battery electric vehicles are going to increase by these numbers, right? And you will not believe, okay, how this is going to increase, because government policies are also going to support them. Battery advancement and cost reductions are also going to increase them. Now, there is a data published in 2023. It clearly indicates in this Energy Conversion Management Journal, it clearly says that this is the battery market in $1 billion, right? This is 2022 and this is 2050, right? Just imagine, this is going to increase by how many x? This is 45 and this is almost 20 times it is going to increase, right? And if you convert it into percentage, this is going to be 2000%. This change is going to happen. By 2030, this is going to increase by 10 times. Clear? So this is the battery market in $1 billion, right? And this is being driven by the growing EV adoption. This is being driven by renewable integration, battery requirement there, and this is having an opportunity of these second life battery which are coming out of this EV, and here it can be used, right? Now, this is the cost of battery, sorry, this is the cost of energy which is going to reduce, levelized cost of energy, and it is an indication that this is possible only with the use of second life battery, because this cost of energy, if we are going to use this fresh batteries, new batteries, right, the cost is going to reduce in this manner, light blue, right? But if we are using this second life of battery, then the cost is going to reduce like this, means 45 to 70, it means around 70 to 75% cost is going to be there, means some more than 25% decrease in cost of the levelized cost of energy due to this second life. So here it highlights the importance of use of second life of batteries for renewable energy integration purposes, right? And making the cost of energy lower. Here comes the share of global market of electric vehicles and renewable energy. Means this EV numbers are increasing, means new batteries will be required more, and after 8 years they are going to be converted into second life batteries, right? And how this market for renewable energy is going to increase by 2050, means if the market for renewable energy is going to increase, then the second life battery opportunity is also going to increase to work with renewable energy integration, right? So here is the opportunity. It says that this EV global market share is going to be 13% 2022, then this 13% is going to 26 in 2030, and this is going to 82% approximately in 2050. Similarly, the percentage of electricity, renewable energy electricity is going to be 30, 61, and 88 in these marked years in comparison to 2022, right? So this shift is clear indication that the technology leaders or the global leaders or the countries, they are committed to shift the vehicles uses and electricity generation methods significantly to reduce greenhouse gas emissions and impact climate changes. Clear? So here comes the scope as an opportunity as well as challenge for use of batteries and second life batteries for impacting the climate change. And this is the a challenge for the modern power system, how we are going to handle these changes and how to making this economy circular, how to making sustainable efforts towards making our power system compatible with these changes. It is a recent report of January 2025 where the government of India, MNRE, they published this diagram. They says that the total capacity at present of the renewable energy is 209.44 gigawatt. And they say that they have added this 28.64 gigawatt in 2024, and they are working on track for the target of 500 gigawatt renewable energy target by 2030. Clear? So what I was showing you in the last slide, that was the global scenario, and here it is the national scenario in case of India, our country. And this is about the electric vehicle adoption. This is a report prepared by for the targets for this 2030. This is a report of some different sources, different stakeholders, where the Niti Aayog is also a part of that team, and they have prepared this with this integration of all types of electric two-wheeler, electric three-wheeler, electric four-wheeler, electric bus, etc. And they have merged that by these years, the annual EV sales is going to increase like this. Clear? And these are two different estimates. One is the estimate of this JMK research given here, and this is the estimate of Niti Aayog, and which are more positive in their forecasts. Clear? So this is again the combined scenario of the EV and renewable energy increase in Indian scenario. Before that, I presented in last slide to that, I presented a global scenario, right? So with this, transportation sector is completely shifting to electrification. And what are the advantages? That this reduces carbon emissions, improves air quality, and combat climate change. Clear? So this clearly indicates that this number of retired lithium-ion batteries from EVs is going to grow in the coming year. It is growing presently also, because a recent study of China says that retired EV batteries in China, historical growth is 2012 to 2018 was 80 times, right? In though 2012 it was 0.1 thousand tons, and it becomes around 8 tons in 2018. And it is projected that by 2040, this is going to between 1,500 to 3,300,000 tons, right? And because the China is an early adopter of the electric vehicles, right? We have started developing this infrastructure for EV adoption a bit later in comparison to China. But we all know that how fast we are moving towards the EV adoption. There are a number of vehicles which are manufactured by the Indian manufacturers in India, right? So here is a big challenge for all of us. And definitely every challenge comes with an opportunity. So the challenge is, how can these batteries be managed sustainably, right? And the answer is, they can be made reuse, recycle, with giving priority to the sustainability, right? And here comes a challenge. We shall try to find out what are the possible new applications of these second life of batteries. So you can find that a IEEE transaction in 2023 that published in its research that the different applications of second life batteries, they have surveyed the papers, made some simulations, and found that renewable energy systems, energy storage stations, light commercial buildings, low speed transportation, and using in residential buildings, all of these you can clearly see that they are for storage purposes only. Storage of renewable energy or excess energy when the energy is cheaper, and use them when either the energy shortage is there or the energy is going to be costlier. Clear? So these are the applications related to the storage only. So here comes the potential market and future outlook about second life battery, right? So there is an estimate that these SLB could generate around 200 gigawatt hour by 2030, and the market is going to exceed beyond $30 billion. Clear? So this is an older estimate which was made in 2019. The things are, or the numbers are much more larger in present scenario. And as you found that the numbers are different also by different agencies depending upon the scenarios considered for their studies. Clear? So we all know that if these second life of batteries are going to be utilized, we are going to have some different type of advantages which may lead us to reduced greenhouse gas emissions, to adopt these sustainable practices in the world as per the requirement of achieving sustainable development goals of the United Nations, and following the government policies. Means as a citizen it is our duty to adopt all those policies which our government are asking us to do, because these governments of the countries, they are under some mandatory requirements of some global scenarios where all the countries are required to perform some common goals, right? You know that United Nations goals are also such type of goals which are forcing each country to reduce the greenhouse gas emission. So there are new technologies, new areas of research which are coming as carbon credit, carbon storage, right? So these are the new terms which you shall learn and make yourself interested in learning towards them. Then I told you with this data that there is significant potential for supporting this RE generation. There is significant potential of second life batteries availability in the coming years, so they can complement each other. In projected contributions of to India's energy infrastructure, these SLBs, they could provide 1300 to 1800 or 1900 gigawatt hour of energy storage by 2038. This is a projected scenario from a research paper listed below. This capacity could support 17 to 39% of daily energy generation from renewable energy. SLB's integration into energy grid is critical to achieving India's RE target, as I have given you by that data shown by the MNRE of Government of India. So this all makes to utilize the second life of batteries for technical purposes or integration of renewable energy support in modern power system. So this is a great opportunity. We shall learn about this, and we shall try to find out more uses, methods, how to use more these batteries, second life batteries in the power system to make their shelf life useful. Challenges in battery reuse, they are aging impact. That is a key factor affecting safety and efficiency. कमलेश जी कितना टाइम है और?
सर आप ले सकते हैं टाइम अभी 10-15 मिनट और.
हाँ अच्छा ठीक है, 10 मिनट में खत्म करता हूँ. 10 मिनट में खत्म. So a key factor attending is affecting safety and efficiency, because aging is a parameter, because we all know that there are different parameters, different components in the battery which give a performance with the regulated operation of all these components. If any one of them is going to have some difficulty or some, you can say that it is damaged or it is aged, right? So this may impact the performance of the whole battery. So safety concern, that is going to affect the safety, because we all know that this battery fire is a very damaging thing, right? And there are possibilities there may be a spark in a single cell or a single module, and that may damage the complete vehicle. You must have seen or read all such cases, right? And there are some safety standards also related to that, but even after that, the mishaps happen. So there are aging impact. They key factors are technical and economical feasibility depending upon aging performance. Degradation trends are unpredictable, affecting feasibility. First life aging history tracking can be determined the best reuse applications, right? And how to track that? How to track the history, right? That's why in few research papers they have used the concept of digital passport for every battery, means a complete register of events which can indicate you or inform you about the events that are happening or happened in past inside the battery, right? Then comes the cell. We know that the different batteries, they are made of multiple cells, right? And these variations in technical state of cells, they are capacity, internal resistance, and voltage, right? And these SLBs, they have a difficulty or negative point that they show variation cell to cell, right? And in case of new batteries, these cell to cell variations are not much, right? So this is a challenge which is to be handled, right? And that is only possible with the use of refurbishing, right? But refurbishing is having a number of events involved in that. That increases the cost also. How this is going to impact the cost? These are the few things which are to be understood. There is a diagram I can show you that this is the price comparison. It clearly indicates that the first life of battery, it reduces to 80% of this thing, its capacity. Then the cost reduces to around 60%, right? And this total cost, which is 60% now, its complete distribution is given as this 7%. If we are going to repurpose it for some new use, then it is based on a study that the SLB price, second life battery price, is 60 to 70% of the new battery life, right? And this SLB selling price is SLB buying cost plus SLB repurposing cost. And if we distribute this repurposing cost, it clearly says that 7% goes to warranty, 5% goes to insurance, 5% testing, 5% capital reserve, 2% renting all those administrative charges here, 29 or 30% is labor, 30% is around general and administration, and again the 16 percentage packaging material for packaging the old cells into a new battery pack. Clear? So there are infinite opportunities to reduce this 30%. How to reduce this labor cost? And if we automate this process here, by using some AI techniques, there are multiple research papers available on this domain which say that how all these things can be automated. Clear? And just to the target is how to reduce these cost components to make this second life of battery more cheaper with some repurposed technology, right? And this is a comparison here. It clearly says that battery price, this is the second life battery price reduction, and this is the first new battery life reduction, right? So these prices year wise are coming down, and it is a good thing that the battery prices for the new batteries are also coming. It is expected that in the coming year, these second life battery use of second life batteries is going to be more economical for its user, right? And this is some distribution for what purposes we are going to use it, but that I will not discuss here. You can find it. Basically, this is an article of this IEEE transaction of transportation electrification 2023 December. You can refer it for your more study purposes. And then there's a paper on this 2022 Energy Journal. It clearly gives you the degradation of lithium ion batteries. What are different mechanisms? They have given that these are the four mechanisms which are primary mechanisms, and what happens in them, and what are their effects, right? So this you can refer for your study. Basically, I will suggest you to go through the paper, right? This author, this Sajan Lal is also a author, Iranian author, right? And he has written a lot of papers on the second life of lithium-ion batteries. You can refer his papers for further study. Then there are components, and all these tabular comparison are given from basis on the based of information of these papers only. So here you can find out, and I can give you an example as a case study that this was presented in a 2019 workshop. Workshop happened in 2015, I think, but it was reported after 4 years. This was a concept of 2015 that the Sunbat project it was developed for the affordable, transportable, safe, and replicable energy system storage using repurposed EV batteries, right? So how it was made? It was made with four batteries which were from a old Volkswagen car, right? And the capacity of each battery was 8.8 kWh, original capacity. This was having AC-DC converters of 20 kilowatt each, efficient power conversion because AC-DC conversion. Battery management system was to optimize energy utilization and safety monitoring. Centralized control was done through SCADA. Energy management system was integrating weather forecasting to protect energy needs, grid demand and supply optimization, human machine interface for user interaction, right? And what services it was providing? It was using a old container of modified maritime container, which we see in these loaded on the ships. And nowadays we see them on the trains also for the long distance goods trains, right? And that has been having the battery storage as well as electronic components. Now you can see the diagram here. This is the container, and this is the internal diagram, and this is the battery pack. This is SCADA system. This is EMS, energy management system, human machine interface, AC-DC converter, right? And it was providing you one fast charger and three normal chargers, right? And this was having a solar panel also for getting electricity from renewable energy resources, right? And this AC-DC converter is connecting it to the grid also, where this EV chargers, when they are not in use, they are capable of giving this electricity back to the grid also. Or if grid power is not available, in that case, using this solar power and this battery storage, they can provide the charging facility, right? So this is a purely sustainable model, right? And it's having a estimated span of 30 years because these applications are not going to be used for higher depth of discharge. It is expected that the depth of discharge will be lesser, very low. So it is fulfilling the challenges of environmental benefits depend on energy sources, that is renewables versus grid electricity. Battery degradation variability affects performance. Battery charge discharge efficiency leads to 17% energy loss, right? So these are the few challenges which were they are facing right now. But in future, they are trying to improve this model with standardization of SLB testing and certification, improved automation in battery refurbishment, and integration of AI-driven energy management. But the most important thing is that, which shall be highlighted here, that it is also having a sustainability benefits of 9% CO2 reduction compared to conventional grid power building. It is supporting cleaner energy storage for EV fast charging stations, reduces reliance on fossil fuel based backup power sources, means not on grid. It can directly take source from energy from the renewable energy, right? And it is working since 2015. Clear? So at almost 10 years, and since then, a lot of new technologies have come, a lot of prices have come down. So it gives you a motivation for developing such things in our country also, in your location also. So that's all for today's session. Now, if you have any question and answers, you can ask right now. Otherwise, if time doesn't permit, you can take my email ID here. It is Asheesh at mnnit.ac.in. Do not forget double E here and double N here, right? So this is double E and Asheesh and double N in MNNIT. You can write me and we can discuss any question. Either it is a new, not covered here or not covered here. That will also be learning for me from your side. Thank you very much.
Okay, सर सर एक क्वेश्चन था, आवाज आ रही है सर?
बिल्कुल आ रही है सर, पूछिए पूछिए पूछिए।
मैं ये कह रहा था कि एक नॉर्मल चार्जर जो होता है वो अराउंड 7-8 आवर्स लेता है चार्जिंग के लिए बैटरी को, इलेक्ट्रिक व्हीकल के लिए,
जी
और फास्ट चार्जर 2 से 3 घंटे में चार्ज करता है। तो क्या फास्ट चार्जर सेफ है, और यदि सेफ है तो इसका क्या चार्जिंग डिस्चार्जिंग साइकिल पे कोई इफेक्ट आता है?
Sir, safety features basically they depend on the current limits, right? Please, you can directly take it. Even if we are not using these EV chargers, you can simply take it as fast chargers for your phone, mobile phone, right? There are certain phones available which are using fast chargers. आजकल देखिए लोग जो भी मोबाइल छोटा होता है और चार्जर उसका उतना ही बड़ा होता जाता है, right? But there is a limitation that you cannot this is the charging limit is basically controlled by the battery management system of the mobile. Even if you are using that high charger, but if the mobile is not competent for receiving that high power, it will charge with a smaller rate, right? So safety is always a priority. Without safety checks, no products are delivered to the market. Clear? So be satisfied, be comfortable, be confident that the products which are being launched in the market, they are safe. Clear? Accidents happen, no doubt. They always happen because there are some compromises sometimes and some faults take place, right? But that's why we are here. That's why they are the sources of learning for us, right? So I hope you got your answer. If it is, if my illustration is not covering, you can come again.
ओके सर, थैंक यू। आपने अपना बहुमूल्य समय दिया, और मैं आपसे रिक्वेस्ट करूंगा कि एक बार आरईसी कन्नौज में आप ऑफलाइन मोड में आए और यहाँ पे लेक्चर लें।
बिल्कुल आऊंगा सर, बिल्कुल आऊंगा। पीछे में यहाँ पे आया भी था एक बार, तो शायद उस
हाँ हाँ
समय
सर,
से
तो
मुलाकात नहीं हो पाई थी।
अपने अपने
लेकिन
डिपार्टमेंट की तरफ से मैं आपको इनवाइट करता हूँ कि जब भी
बिल्कुल
आप आए घर
बहुत
तो जरूर आए घर।
आपका बहुत
ठीक है
बहुत धन्यवाद। मैं जरूर पहुंचूंगा सर। मुझे अच्छा
जी
लगेगा कि बच्चों से मिलने में और आप लोगों के साथ संपर्क करने में, सहयोग करने में। जी
जी, ओके सर, थैंक यू सो मच सर।
थैंक यू सर। मैं जा सकता हूँ?
जी जी सर,
थैंक यू।
ओके, थैंक यू।